So enols and enolates. We saw just a moment ago that OH minus is able to catalyze that enol keto tautomerization. But how could that be, right? I mean, we have OH minus. How basic is that? The related conjugate acid to that would be H2O, and H2O has a pKa of what? Yeah, about 16-ish. How could that deprotonate that? What do you guys think this CH bond, what would its pKa be? All right, so you paused that, you thought about it a little bit, you've made a selection. Yeah, and I'll bet a lot of you kind of maybe potentially related it to CH4, right? We have CH4 on our pKa list. It's an sp3 hybridized carbon atom bonded to a hydrogen. It has a pKa of 50. And we know that that's not acidic. That's kind of the opposite of acidic. But we know that this has a pKa of 16, so that means that this base is not even close to as strong as this base. And let's just define that really quick. So stronger acids have what type of conjugate base? So if you have a strong acid, you have you already wrote something in, you paused it, wrote something in. Stronger acids have weaker or more stable, stable conjugate bases. So this is a much stronger acid, so this is a much weaker base than something like that. But that being said, how does that relate to this molecule then? OH minus, there's just no way. It's not able to deprotonate CH4 because that is just not acidic enough for it to do that. But we know that this must be able to deprotonate that because we've already said that it does facilitate that equilibrium. So how close do the acids bases have to be in equilibrium? So again, let's look at that real quick. So if we have OH minus and we know that there's at least some of the material over here, there's at least some O minus over here, or C minus over here, and H2O. And we know that this pKa, like we said above, is 16. So what the heck is this pKa? How close do they have to be for the equilibrium to be even discussed, right? All right, I'm going to reveal the answer you've all been waiting for. What is the pKa of this CH bond? It turns out that it's 20. So why is it 20? What makes it so much more stable? And we can write that down here too. So this pKa is 20. Why is this carbon anion so much more stable than that carbon anion? Well, again, we already talked about it when we showed the enol keto tautomerization, but essentially the anion there is delocalized. It's not just a carbon anion, it's also an oxygen anion. And we know oxygen is much more stable holding a negative charge. It's more happy with that because it's more electronegative than carbon. So how much does that delocalization onto a more electronegative atom lower that pKa? Well, it looks like it lowers it 30 pKa units. So that's 10 to the 30th as far as the equilibrium there. This pKa is 20. This pKa is 16. And really it's somewhere between about so what's the largest difference there can be and it still be a useful equilibrium? So being a useful equilibrium means that there is at least some amount of material on both sides of the arrows. And it turns out that that's usually somewhere between 5 and 7 pKa units difference is where it will no longer have anything on that side. So if we try to deprotonate CH4 with OH minus, there's just literally none of it on that side because this is not a strong acid at all. But when we have the CH bond here, being only 4 units different than water, OH minus is at least able to deprotonate some of that. Why is it important for us to be able to kind of have a rough estimate of what these pKa's are, of how acidic a CH bond is that will form an enolate equivalent? Well, it turns out that any enolate equivalent is going to be able to act as a nucleophile in its enolate form, and that's what this is called. So the enol is when this OH is protonated. This is called the enolate. The enolate. And any enolate equivalent will be able to add to an electrophile. So what we're going to do more now is kind of talk more about what enolate equivalents there are and how can we kind of estimate those pK values. Okay. So we just learned about how ketones have a relatively acidic CH proton and the alpha carbon to the carbonyl. So now we're going to kind of take this a step further. We had just a ketone. Now we have a 1,3 diketone. So 1, 2, 3. That's their relationship to each other is 1, 3. And the question is, well, what would you expect the pKa of that proton right there to be? Again, stronger acids have more stable conjugate bases. So take a minute to pause the video, draw some structures out, and then try and approximate the pKa here. Okay, you did that. Good job. So how do we figure out how acidic something is? We look at the stability of that conjugate base. So if we remove that proton somehow, minus H+, we would have a structure that looked like this, right? A negative charge and a lone pair right there. We'll even draw a base deprotonating that just to show how it got those electrons right there. So how stable is this negative charge? Well, it has that same type of stabilization that we saw with the enolate that we just talked about, where we can move the negative charge up to the oxygen. That would give us a structure that looked like this. So is that it? Is that the only resonance structure we can draw to show that conjugation? No, right? We can also put that negative charge on the other oxygen, and we're going to do it directly from this structure where we will draw those electrons going down there to reform the pi bond. This pi bond is going to move to between those two carbons, and then that pi bond is going to break, go up to that oxygen. So we have here the negative charge up there and that carbonyl right there. This conjugate base is more stable than just from a single ketone. So this is more stable. So what does that mean for the pKa of that? That means that if this is more stable, that's going to be more acidic. So the answer here would be less than 20. And it turns out that the pKa of that proton is actually 10. So it drops an additional 10 units by having a second oxygen that the electrons can delocalize onto. So 1,3 diketones, pretty acidic proton in between the two carbonyls because of that extra delocalization. And we can have 1,3 diketones that, so these are the enolate forms. 1,3 diketones also have that same equilibrium, right? So this would be the 1,3 diketone, and it can tautomerize to the 1,3, or sorry, so this is the keto form, and this would be the enol form. And it turns out that in a 1,3 diketone, the equilibrium lies, this says lies, to the enol side for a few reasons. So if we wanted to draw our arrows in here, we would draw something like that, showing that there's a greater amount of this, and this is a pretty good equilibrium for like looking at it with NMR. If you look at these two species using this molecule with NMR, you'd see a ratio of about 70% of this form and 30% this form. So it lies to this side, but not to a drastic extent. It's only 20% higher than 50-50, right? So why does the diketone lie to this side? Well, what is more stable about this system compared to a standard enol? So think about that for a second and maybe get some hints from these bullet points. Okay, so you've done that. Usually people get this first one. At least someone in the class usually raises their hand when we're face-to-face. But blank pi systems are more stable. Well, what's different about this pi bond than a pi bond like that? Well, this pi bond is conjugated, right? It overlaps with this pi bond because we have p orbitals here, 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 and here. So that is a conjugated pi system. Conjugated pi system. And conjugated pi systems are more stable. We saw that a lot, both in the aromaticity chapter and even in the chapter before that where we were just talking about conjugation. The other thing that people generally don't get, we don't really talk about this much, is that the molecule has an intramolecular hydrogen bond. And so hydrogen bonds are something that molecules do to be more stable. Bonding is something that things do to be more stable, and hydrogen bonding is just kind of a partial bond. So how does that happen? Well, we have this carbonyl that's right next to this OH bond, so it turns out that it forms a partial hydrogen bond. So this is a full OH bond there, and this is a partial hydrogen bond that stabilizes that structure. So those are the two reasons that in a keto-enol tautomerization with a 1,3 diketone, things look a little bit different. Things are to the enol side, and it turns out that I labeled this a little bit wrong. This is actually, I just looked at my notes, this is 24%, and this is 76%. So same story, but I just wanted to make sure you had the real numbers. So we can form enols with these 1,3 diketones as well, and they're going to form even faster because that enolate is more stable and the enol is even more stable.